Let's take another look at what we were doing when we were comparing the results of various algorithms. Here we were considering 3 algorithms for controlling a self-driving car, trying to keep it about 50 meters behind the car in front of it. One thing we did was we took the average of the errors, and we wanted that to be low, of course. But what does low really mean? We'd say these are reasonably low. Is -9 low? Well, if low means as close to negative infinity as possible, then -9 is lower than these, even though that's really not safe. So when we say low for average error, we actually meant close to 0 rather than close to negative infinity. And so to avoid counting the negative as lower than these others, we could square each of the average errors. That's different than averaging these squared errors, but let's go ahead and do that here. So we can say, if I take this average error and square it, I want that to be low. So let's write that here. And the average error is called the bias. So this is the square of the bias, and we want the square of the bias to be low. We also wanted not too much wandering around. Large waves are worse than small waves. So we also talked about the standard deviation of the errors. And we said that wasn't a great idea because it ignores the bias. I'm going to make a small change to the standard deviation formula here. I'm going to use the standard deviation for a population that divides by n instead of n-1. It's not a big deal, but I mentioned it here as well. So we want the standard deviation to be low as well. So we could also take that, and just to get consistent units, we could square the standard deviation. And the standard deviation squared, another name for that is variance, and we want that to be low. So we have these two things we want. We want the squared bias to be low, and we want the standard deviation squared, or the standard deviation, to be low. And sometimes when we want two things to be low, we can just add them and then want that to be low. So here I can say just take the squared bias and add the squared standard deviation or the variance, and then we can say that's the number we want to be low. We want to be right on average, that's the squared bias, and we want to not wander too far away, that's the squared standard deviation. Do we notice anything about these numbers, 42, 6.5, and 101? Well, actually, that's basically the same thing we have here. In fact, it's exactly the same. So what we've discovered is the mean squared error is actually composed of the squared bias plus the variance. So that's actually a general principle. It's not just to this particular situation. There's an algebraic proof of it here in Wikipedia that the mean squared error, after all this algebra, is the variance plus the squared bias. This is related to something that's more common in machine learning called the bias-variance trade-off. It's not the same thing as the bias-variance trade-off, but that is a very important thing in machine learning in general, and we'll talk about that later. Now, one thing hardly anyone talks about here, we just added the squared bias and the squared standard deviation as if they're kind of equally important, but maybe in some applications you would care more about keeping standard deviation low, and so you might multiply the standard deviation or the squared standard deviation by something and then add it to the squared bias. And you could multiply it by 4 or 19 or whatever, or you can multiply it by something less than 1 to give it less weight than the squared bias. So this idea gives you more options for which things are more important to you in expressing that in math.